Hey there, this is Mrs. Tollison with your review for Layers of the Earth, Continental Drift Theory, and the Theory of Plate Tectonics for our upcoming test. As in the past, it's recommended that you have a paper and pen with you so you can take some notes if you need to, or maybe your notebook so you can highlight or add things to your notes. Feel free to stop the video at any time to look over what's on the screen or replay different sections. And watch it as many times as you need to help you get ready for the test. Alright, so we talked about that layers of the Earth. There are 4 main layers of the Earth, and from outermost to innermost it goes crust, mantle, outer core, inner core. Some of you in elementary school may have just learned that the core was one thing, but we've divided it into 2 because the outer core and the inner core have very different qualities. It's not the same throughout, so we separate it out into 2 different parts. This picture is not shown in proper scale. We also talked about the fact that if you could drill from the crust to the center of the Earth, which you cannot, you would notice that the temperature and the density increase as you move from the crust to the inner core. And even though we haven't been able to drill more than a few miles into the crust, one of the reasons that scientists know so much about the inner layers of the Earth is by studying seismic waves or earthquake waves. The way those waves kind of travel through the layers and bounce off other layers gives scientists an indication of what those materials are that make up the layers, how thick the layers are. So that information is gathered from seismic waves. So when we look at the layers of the Earth, we know that the outermost layer, which is the crust, is the thinnest layer. It is very thin in relation to the overall size of the Earth. The continental crust, which is the crust that's underneath the land, underneath the mountains where we live, what we stand on, is made of granite. And this type of crust, the continental crust, is thicker than oceanic crust. Oceanic crust, which on the picture is right here under the ocean, is thinner than continental crust, and it's made up of a kind of rock called basalt. The mantle is the thickest layer of the Earth. This is the layer that contains the convection currents that help move tectonic plates. We'll talk about that more a little later. It is made of magma, which is molten rock. The asthenosphere, which is the kind of towards the top of the mantle, is made of a rock that flows very slowly. So it is a solid, but it's a solid that can flow kind of like putty or tar, and this is what causes the movement of tectonic plates. The outer core is made up of mostly liquid iron, which I put the elemental symbol there, which is Fe, and nickel, Ni. The movement of material in this layer is what causes Earth's magnetic field. Okay, and Earth's magnetic field is important. We'll talk about that a little bit more when we talk about space science. It's what protects the Earth from solar wind from the sun. The inner core, even though it's the hottest layer, it's made up of solid iron and nickel. So there's so much pressure from all these thousands of miles of material above the inner core that's pressing down on it. That means it can't be a liquid. It's a solid because the particles of iron and nickel are pressed so closely together that they can't flow like a liquid. So the lithosphere, which is made up of the crust and the uppermost part of the mantle, it's a rigid, rocky layer, and that's what's broken up to make the tectonic plates that we'll talk about when we talk about the theory of plate tectonics. And the movement of these tectonic plates is caused by convection currents in the mantle. Okay, convection currents, if you remember, we looked at a lava lamp in class, and the same thing that happened in the lava lamp is what's happening in these convection currents. This part of the mantle that's down here nearer to the outer core is hotter. The rock gets heated up and it starts to flow because heated material is less dense than cooler material. So the less dense molten rock starts to rise up through the mantle. As it gets towards the top here, nearer to the crust, it cools off, so it becomes more dense, and then it starts to sink down where it'll get heated up again, and then it will start to rise, and it just continues this circular or cyclical movement, just like we saw in the lava lamp. And so that movement of rock material is what pulls along these plates that are here at the surface. So the theory of continental drift, or continental drift theory, either way, it doesn't matter how you say it, it's the same thing. In 1912, a scientist named Alfred Wegener, he studied meteorology first, but in doing that, he discovered, as we talked about in class, he noticed a lot of things about the Earth and the continents, and he became very interested in trying to understand what he was seeing and proving his theory, which he eventually came up with, that the continents were once all part of a single giant landmass called Pangea, or Pangaea. And this word literally means all Earth. So all of Earth's land masses were clumped together in one big supercontinent. And that over time, over about 250 million years, they've slowly drifted apart to where they are today. And his proposal was called the theory of continental drift, or continental drift theory. Now, he had lots of information that he went and he gathered to support his idea. Things like the fact that the continents looked like that they all fit together, like puzzle pieces. That similar fossils were found on continents that were now far away, like Mesosaurus and Glossoteris. And there's no other reasonable explanation for how they could have traveled such long distances. Because Mesosaurus, we talked about, was a small freshwater reptile, and it's found in South America and Africa. And it doesn't make sense. It could not swim across the whole Atlantic Ocean the way the continents are today. So it makes sense that at some point in the far distant past, those two continents were next to each other when Mesosaurus was alive, and then after Mesosaurus died and became fossilized, the land ripped apart to where it is today. He also noticed that landforms, such as rivers and mountain ranges, would match up across the continents if you could move them back together. Like in the video that we watched in class, similar mountain ranges are found in North America and Northern Europe. They're made up of the same kind of rock. They're made up of rock that's of the same age. So it makes sense that at some point in the past, those two areas were next to each other, and that when the continents pulled apart from each other, some of the mountains moved with Europe and some stayed with North America. He also discovered some climate and glacier evidence. There's evidence of glaciers, and we talked about striations on the rocks. When the glaciers, which is just a huge river of ice, moves across the land, it scratches up the rock as it passes over it. And there's evidence of that in what is now tropical rainforests of South America and Africa. And the only real logical explanation for that, if there's no ice there now, there's no glaciers there now, is that at some point long ago, those continents were in a location on Earth that was much colder, so that glaciers traveled across them at that time. And now where they are now, there is no glaciers. Also evidence of tropical plants. Again, in the video we watched, it talked about bituminous coal. It's made from tropical plants over time. They die, they get compacted and pressed down and eventually become coal. But bituminous coal has been found in Antarctica, Northern Europe, North America, in areas that obviously do not have tropical plants right now. So if there is bituminous coal there, it means that at some point a long time ago that those countries were, or those continents were in areas that were much warmer. So again, this glacier and climate evidence was the final piece of evidence that Wegener found to support his idea that the continents have not always been in the locations that they are today. They were once at a different arrangement, and they moved over time. Unfortunately, most scientists of his time did not believe Wegener because there was one really important piece that he couldn't explain, and that was how the land masses moved. he couldn't explain that one thing, and because of that, a lot of the other scientists really didn't believe him. And he spent the rest of his life trying to figure out what that missing piece was, but he never did. So when Wegener died at the age of 50, people still did not, many people still did not believe his idea. So this image here is just showing some of those pieces of evidence that we just talked about. So again, here's the glacier evidence. If you looked at South America and Africa and even parts of India and Australia here, you can see evidence of the scraping marks left by glaciers moving across the land. Okay, and here's Antarctica down here. But it doesn't make sense in the arrangement that the continents are now, but if you put them back in the arrangement they were in Wegener's Pangea, you can see these striation marks or these scratch marks. It kind of lines up perfectly that there was a glacier that covered all of these areas. And again, here it's talking about the distribution of Paleozoic rock types based on the climate of the time. So again, this is Pangea. It makes sense if all of these continents were much closer together than they are now. And then here's the evidence that we did in class, which you have a map that looks kind of like this on page 151 in your notebooks, with the evidence of Mesosaurus and Cynonathus and Glossoteris and Lystrosaurus, that these different plants and animals, evidence of them has been found on these continents, and if you arrange them in the way they are here, it makes sense that sometime in the distant past, maybe like 250 million years ago, these continents were all close together. So the theory of plate tectonics takes what Wegener found, all that information, and it adds the piece that he could not explain, which is how the plates were moving. So in the 40s, 50s, and 60s, scientists were looking at the ocean floor and mapping it and finding out information, and they discovered some evidence that proved that Wegener was right all along. They started to realize when they were taking some samples that the ocean floor, the crust of the ocean floor is a lot younger than continental crust. And so they didn't quite at that time understand what was going on, but over time they came to realize that the ocean floors are spreading apart and that new ocean crust is being formed in a process called seafloor spreading. So this picture here shows this process happening. What happens is you have magma, which is melted rock in the mantle. It's rising up between these two tectonic plates as they're moving apart. And we can see the arrows here showing that they're moving apart. As that happens, new rock is being formed right here at the mid-ocean ridge. So the newest rock is always found right here at the center by the mid-ocean ridge. As new rock is continuously being formed here, it's pushing the two plates further and further apart, kind of like a conveyor belt. So the newest rock is always going to be found here at the ridge, and as you move further and further away, the rock is older and older. Now, if this is happening, why you would think that the Earth would be getting bigger and bigger if new crust is being formed all the time in the ocean. But just because there's new rock forming here, there's another process that's the opposite of that. Older rock is being destroyed in other parts of the ocean crust. So basically the ocean crust is being recycled. So older ocean crust is destroyed at what are called subduction zones. This is where you have the oceanic crust, or the plate that's made up of oceanic crust, sinks or subducts below either another slab of oceanic crust or under a slab of continental crust. That's what I'm showing here. We've got oceanic crust and continental crust. So here you see, here's the mid-ocean ridge. So here's the newest rock material. Rock is moving away, and eventually this oceanic plate is subducted or forced down into the mantle. Over time, that rock gets melted. It forms magma. We also often find volcanoes near subduction zones, because this molten rock that forms magma then rises up through the crust and can erupt at Earth's surface. Um, this process of recycling older ocean crust is the reason why the ocean crust is so much younger than the continental crust. It never gets really that old. I mean, it can be hundreds of millions of years old, but it's not going to be billions of years old like the continental crust, because after a certain period of time, it's forced back into the mantle where it melts and gets recycled. So this process keeps happening over and over again. And in this picture, these two plates are moving towards each other here. We've got the ocean crust is moving towards the continental crust, and that's a convergent plate boundary. So all of that evidence about, about seafloor spreading and mid-ocean ridges led to the current theory of plate tectonics, which states just that the Earth's crust and upper mantle, which makes up the lithosphere, is broken up into large slabs called plates, and that these plates move slowly across the Earth's surface because of convection currents in the mantle. So we talked about that a little earlier in the presentation, but here you can see these convection currents. You see it's moving in this circular pattern, which is moving this continent in this direction. This convection current is moving this way, which moves this plate in this direction. So these two plates would be moving apart. And then here, again, if this plate's moving, this circular motion is moving this plate this way, this circular motion is moving this plate this way. So that pulls these two plates together. So not all of the convection currents move in the same direction. Some of them move in such a way to move plates towards each other, and some of them move in such a way to move plates away from each other. So there are three main types of plate boundaries that we've talked about the other day in class. There are ones that are called convergent boundaries. This is where two plates move towards each other, or they collide, they crash into each other, which is shown here with the two arrows pointing towards each other. When that happens, you can get mountain building when two continental plates crash into each other, like with the Himalayas, where Mount Everest is. That's how that was formed. You can get subduction zones, like we just showed, where ocean crust goes and sinks below continental crust, and you end up getting volcanoes there, recycling old ocean crust material. So you can get mountains made, old crust is destroyed. Divergent boundaries, this is like this picture shows here, where two plates are moving away from each other or dividing. That's when you get that mid-ocean ridge, which is underneath the oceans. But this same process can happen on the land, and you can get something called a rift valley. The Great Rift Valley in Africa is an example where the eastern part of Africa is pulling away, or part of East Africa, excuse me, is pulling away, and eventually, and I don't know, who knows how long, it could separate itself completely from the continent of Africa. And finally, transform boundaries, which is shown in this picture here. This is where two plates move horizontally. They slide past one another. And this is the kind of action that leads to earthquakes. And you get fault lines, like the San Andreas Fault that we looked at a picture of the other day in class. So these are the three, when the convection currents are moving the plates, these are the three different possibilities. It can be divergent, convergent, or transform. The thing about tectonic plates is they're moving in different directions in different speeds with relation to each other. So you have a lot of these interactions, and scientists have been able to kind of map the plate boundaries and see where the different plates are on Earth by looking at a lot of earthquake and volcano evidence, because most earthquake and volcanic activity happens where plates are interacting with each other, where they're moving towards each other, away from each other, sliding past each other. So scientists have used a lot of that information to figure out and be able to map all the plate boundaries across the world. So that's it for this review. Go back and watch it again if you need to. Watch portions of it if you need to. Look over your notes. Look over the Quizlet links that you have. And there's a couple of other video links that you have available to you that you can review. And I will see you in school tomorrow.